Hello, everyone, and welcome to the second lecture. This is the lecture called Introduction to Resonance. And so, resonance is going to be a topic that you're going to see throughout all of OChem 1 and OChem 2. It is incredibly important, which is why we're tackling it a little earlier than most classes would. But the way that we do this should come in the best order possible for you all to learn how all this works. And so the first thing I want to talk about whenever we get into talking about resonance is we need to discuss what is an electron, which sounds like a very simple question, but it's incredibly important because essentially electrons are the basis of all of organic chemistry. It sounds very silly because I know we just talked about it being carbon and hydrogen, but these little dots, which are these little electrons, are very important. So an electron is just essentially a negatively charged particle, right? And so these negatively charged guys really like to go to places that they are lacking, which is why previously we talked a little bit about what is called the octet rule, where things like to have 8 electrons. And if they don't, then they need more electrons. And it's usually to balance out charge. And so essentially, all atoms have these things, right? Every single atom has electrons. And depending on, of course, as we saw last time, how many valence electrons they have, that is going to determine how many they start with and how many they need. So every atom has electrons, and every atom needs electrons. This is the basis of organic chemistry. And so whenever we're talking a little bit about resonance, we actually get to the point that these matter a lot. And so essentially what we're looking at is this thing called resonance is the movement of electrons through pi systems, right? So this movement of electrons is a flow. It can move from one atom to another. And it usually occurs through these things called pi systems, which happens a lot with what are double bonds. And whenever we're talking about resonance, the first thing that we actually need to understand is charges. And so last time we talked a little bit about formal charges, but we need to talk about what they actually mean. So essentially, if we're thinking about formal charges and we're looking at something like a minus charge, right, what this means is it's actually an excess of electrons, right? So those, by the way, every time you see this E negative, that means electrons. So it has an excess of electrons, which means that it wants less. It wants to get rid of electrons if it has a negative charge, because remember, these electrons are negatively charged themselves. Whereas on the other side of things, if you have a positive charge, this means it has a lack of electrons, which means that whatever atoms have this, they want more. And so sometimes atoms can get these through electron movements, because you can imagine that electrons will go from a place where there is a negative charge to a place where there is more of a positive charge. So that is what's going to take us into this concept of resonance. So in order to kind of visualize what resonance actually is, we're going to start out by looking at an example of something that can perform resonance, and then we're going to talk a little bit about what that actually looks like. So our example is going to be this compound here. It's going to be CnOH2 minus, right? So this whole thing has a negative charge. If we go through and we count up the valence electrons for this, right, we know that carbon is going to bring us 4, nitrogen is going to bring us 5, the oxygen will give us 6, the hydrogens will give us 2, but we also have this negative charge here, and whenever you see a negative, that is also 1 electron, right, because each electron is negatively charged. So that means that we have an extra 1 here, and if we add up all of that, we end up with this Lewis structure should have 18 electrons. So let's go ahead and let's draw out a Lewis structure that would have, of course, these qualities. So looking at this, we want to put that carbon in the middle. It's very important. And we have this NOH2. So essentially, if we wanted to kind of fulfill all of carbon's bonds, we want to give it 4. And looking at this, it's looking like we can do a nitrogen and oxygen. And we could put 2 hydrogens here, but we know that the oxygen wants 2 bonds, right? And we can fulfill that by giving it a second one to that carbon. The nitrogen wants 3, and although we can't really give many more to this carbon, we can give it a hydrogen, and like we saw before, it loses that other hydrogen because now it already has the 4 bonds with the oxygen. Counting this up, we have 2, 4, 6, 8. We have 10 electrons shown. We know that oxygen needs its octet, so there'll be another 4 there. And then nitrogen also needs its octet. It can't share any bonds with carbon in this case, so it'll also have to have 2 lone pairs. And so we do know that this will be negatively charged. And if we do our formal charge equation, right, looking at this nitrogen here, formal charge is it wants 5, it has 2 bonds, and it has 4 unpaired electrons, which means the formal charge of that nitrogen, that is where our negative charge is. So we can put that right there on the nitrogen. So we have this structure here, right? And this structure has a negative charge on the nitrogen. Now, like I said before, we're looking at this thing called resonance, where up here we see that electrons like to move from the negative to the positive, right? And so looking at this, there aren't really no positive charges shown, but we can perform resonance by sharing this negative charge between multiple atoms. So essentially, these electrons that are on this nitrogen can move to form a double bond beside this carbon, right? So essentially, what we're seeing is the lone pair here, which is LP, is becoming a double bond. And then with that, you can imagine that if that's becoming a double bond right there, carbon would then have 5 bonds. And that's not essentially possible, right? Because we'd be violating the octet rule. We'd be giving it too many electrons. But we do have another double bond up here by the oxygen that can also move. So this is essentially the double bond becoming a lone pair. And this is the basis of resonance, because if we take a look at what this does, we're going to draw an arrow right here that has 2 heads, and this is called a resonance arrow. And so what this is saying is we're essentially looking at the difference between these 2 structures, and they are called resonance forms of one another. And so what this is going to look like is now we have the hydrogen bound to the carbon. We now have a double bond to the nitrogen, right? Because that nitrogen made the lone pair into the double bond. It still has a single bond to the hydrogen. It still has 1 lone pair left over. And now the carbon lost its double bond to the oxygen. It is now a single bond. And so the oxygen now has an extra lone pair. So beforehand, the nitrogen had the negative charge, but if we look at it now, the oxygen will have the negative charge. So these are what we call resonance forms. And the definition of these is essentially it has 2 criteria, or well, I guess 3 criteria total. The first criterion is that electrons have moved. And so that just essentially means that they are in a different position, right? They just have to have moved either from one atom to another or from essentially uh, double bonds to another. So they've gone to different places. The second criterion is that all of the atoms stay in the same place. It's not a resonance form if any of your atoms have moved. So looking at these structures up here, we still see that we have, the hydrogen bound to the carbon is bound to both the oxygen and the nitrogen, and the nitrogen is bound to the other hydrogen. So none of the atoms had actually moved. The third criterion here is that both things you show must be valid Lewis structures. If they are not valid Lewis structures, then sorry to say, but they cannot be resonance forms. And what we mean by valid Lewis structures is essentially things still need to fulfill the octet rule as best they can, right? We started out with everything with octets up top, everything ended with octets, everything is happy, right? There's nothing with an overfilled or underfilled octet. So this is resonance. And there's a couple other things that we need to point out here. And the first one is what the heck are these arrows, right? So we have to ask ourselves, what is this and what does it mean? So essentially, what I wrote in the red and orange up there are what these mean, right? The first one means the lone pair becomes a double bond. The second one means a double bond becomes a lone pair. But what this arrow is overall is these are what we call curved arrows. And curved arrows show electron flow. So they show how electrons are actually moving. And what they do is essentially the arrow is going to have a little bit of a curve to it, and it's going to show on the spot where it starts. So what would be this tail end here? This is where the electrons are coming from, or where the electrons start, right? So in the case of these arrows up here, this first one, we can see the starting point right here is saying that the electrons are coming from the lone pair. Versus the one over here, we can see that this one's starting point is by the bond, which is telling us that the electrons start and come from the bond. The end point, on the other hand, this spot right here, this is saying where the electrons end, right? So where they end up being after all is said and done. And so if we look up here, we see that the arrow is pointing towards the oxygen, right? It's kind of pointing towards the lone pair, but the lone pair belongs to the oxygen already. So it's essentially pointing towards the oxygen. So it's saying that the electrons from that double bond go to the oxygen atom. And then with this lone pair from the nitrogen, it's showing that the electrons from the lone pair of the nitrogen end up forming a bond between the carbon and the nitrogen. And so these electron flow arrows help us tell a story about how electrons are moving through a system. All right, and they're very important because these end up becoming a big part of not only resonance, but of what we call mechanisms later on. Because again, organic chemistry is all about the electrons, where they go, what they do. But essentially, we have to understand the purpose of them moving. So we have to ask ourselves, why do the electrons move? Right? That's the next thing that we need to focus on. So why do electrons move? Well, it has to do with one thing and one thing only, and that is stability. So the way you can think about this is negative charges are inherently unstable, right? That's the first important thing that we need to write down. And I'm going to put it in red because it is very important. Charges are unstable. And so if we're able to not have a charge around, that is going to make things more stable. But even moreover, we can also say that sharing a charge helps stability, right? And so if we're looking at this resonance structure that we have up here, the nitrogen starts with a negative charge, the oxygen ends with the negative charge. That means that essentially, since these electrons can move both directions, right? They can move in the way that we show them here, or on the other side of the map, they can do the exact opposite and return to their original position. We're saying that the charge here is shared amongst both the oxygen and the nitrogen. And so that is essentially making this structure more stable to have that negative charge. And so the way we show these sharing capabilities and how we show that stability is through what we call a resonance hybrid. Hybrids show essentially what the actual structure looks like. Because in reality, although we show these structures having these specific charges there, that is not necessarily true. So if we're thinking about that structure that we just had drawn, right, I'm actually going to quickly copy this whole thing down here. Oh, whoops. Because it is very important for what we're trying to show, right? We can take this, we can copy it, we can bring it all the way down here, paste it. There we go. So essentially, the hybrid of this is going to be the mix of these two structures. So if we take a look at what that means, we're going to draw a Lewis structure that shows all of the atoms connected in the appropriate order, right? So we still have our hydrogen connected to carbon, carbon connected to oxygen, nitrogen, nitrogen connected to hydrogen. However, the things that change we're going to show in dotted lines. So we see that in the original structure, there is a double bond between the oxygen and the carbon, but in the ending structure, there is not. And then the same thing with the bond between the nitrogen and the carbon. In one structure, there's a double bond, and the other, there is not. So in the resonance hybrid, we actually show these as partial bonds, which are dotted. And so these partial bonds are just saying that they're kind of a double bond, they're kind of not. It's like a 1.5 somewhere in between. And then we also take the lone pairs that are always present. So the oxygen always has at least two lone pairs. We show those. And then the nitrogen always has at least one lone pair. We show that. But the other lone pair that's generated in both cases is what contributes to the negative charge. And so how we show that is we add in these partial charges on the atoms that have the charge. So in one case, the nitrogen has the negative, and the other, the oxygen has the negative. And so we show these little delta symbols that I have here in orange with the charge, which is a minus, so that's why it is a delta minus, on both the nitrogen and the oxygen. So these partial charges are showing the reality of the situation, right? It is not that the oxygen has a full negative charge and the nitrogen has a full negative charge. It's that they are sharing a negative charge between both of them that shows that it is partial. It is not a full negative charge. And so this right here is what we call a resonance hybrid, right? This is the hybrid structure. So it's showing how those electrons are being shared. So this is kind of the basis of how resonance works. We're sharing electrons and it makes structures more stable. And there are three different types of resonance that we're going to be seeing throughout this course. And so I want to point those out to you so that everyone is well aware of these and you can actually start to recognize them as you go along. So we're going to ask ourselves, when do we see resonance? Because this is just a single example, right? This is not a good way of saying this is always going to be when we see resonance. So we're going to chop it up into three different sections, right? And we're going to show you resonance structures that deal with all three of these. So the first type of resonance, we'll call this number one, is where you have a lone pair with an adjacent atom that has a double or triple bond. So an adjacent atom that has multiple bonds, right? And we'll even say double slash triple. And this is a good example of what we saw just a second ago, right? We see that in this situation, oops, we have that nitrogen that had a lone pair And then adjacent to it is this carbon atom that has a double bond, right? So the important pieces of this are you have the double bond, you have the lone pair, and they are on two separate atoms. One is on the nitrogen, one is on the carbon. That is one example of when we can see resonance. And as we've seen this resonance form, so I'm not going to go over it again. But we know that the negative charge can move between that nitrogen and the oxygen. The second time that we can see resonance is when we have a positive charge next to an atom with with multiple bonds. So let's take a look at an example of this. So this time I'm just going to draw out a Lewis structure. So we're going to take this set right here where we have these three carbons, and we're going to draw in some hydrogens to make sure that just about every atom is happy. However, this carbon right here is going to have a positive charge. So in this situation for resonance, we have a positive charge. And if you remember from beforehand, we had always said that the negative charge where the electrons are has to move towards the positive. So we have to ask ourselves, where are the electrons here? They're not in the positive charge, right? Because if we think about what this positive charge means, this carbon right here is lacking an octet. And so with that, it's not very happy, right? It doesn't like not having an octet because it only has six electrons around it. And those six are in the three bonds because each of those bonds contribute two electrons. So there's clearly no electrons on that carbon to give. The only electrons that we can see are within this double bond over here, right? It's like we've seen many times before, where each of these double bonds also has two electrons. So what we can see happen is the electrons from this bond can move over and form a new double bond between these two carbons to give that carbon with the positive charge an octet. But what you'll notice is as it does so, taking away two electrons from this carbon is going to take away its octet. All right, so we're going to take away two electrons, and then we're going to lose the octet. Now, normally this isn't a good idea, right? Because missing an octet is bad. But what you can think about it as is now we're going to have these two carbons double bonded together, right? Because we've moved the double bonded electrons to the other carbon position. We have this carbon over here that now only has the three bonds and it has a positive charge. Versus this one over here now has four bonds, it has a full octet. So these are resonance structures here. By the way, that is what those brackets mean. Anytime I put those down, it's just showing that is resonance. But if we think about this as a hybrid, right, we have all three carbons. We look at where things were and where they go. So remember, all of our atoms have to stay in the same place. So all those hydrogens have to still be connected. And we know that the double bond moves between the two. So there is our dotted double bonds between both. And then in one structure, one carbon has a positive charge, and then the other has a positive charge. So we're putting down those partial positive charges to show that, okay, in this resonance hybrid, we're essentially saying that just like the previous one, where the negative charge was being shared amongst two atoms, the positive charge is now being shared amongst two atoms. So essentially what we're saying is we're actually, even though we're losing an octet in one of the resonance forms, we are sharing the missing octet. So it makes it feel less like one of the atoms is missing an octet. Maybe they have eight sometimes, maybe they don't have eight sometimes. But this is still more stable than just having a positive charge. Suffice to say, this is our second type of resonance, right? A positive charge next to an atom with a double or triple bond. Our third type of resonance, which is actually how we're going to end this lecture, is when you have an atom with a positive charge adjacent to an atom with a lone pair or a negative charge. So what is this going to look like? Well, we're actually going to go ahead and draw out another Lewis structure as an example. So for this one, what we're going to say is, all right, this oxygen here is going to have its octet. It'll have a negative charge. This carbon will not. You can imagine here, this one's pretty simple, right? The carbon wants another bond so that it has four. The oxygen has too many electrons. You can balance out the charges. Because if you take one of these lone pairs and you make it into a double bond, what you'll essentially do is you've taken away a lone pair from the oxygen, so now it only has two. The carbon has now gained a double bond, and so now it has four, and we end up in this neutral form. Right? This is a good set of resonance because it's very obvious what we're seeing. Right? This product is much more stable because it is neutral. And as we see beforehand, it started out with something that is missing an octet, but it ends up with everything happy with octets. All right. So that's whenever you have like a negative charge adjacent to a positive charge. The other way is if we had something very similar, where let's say we had this situation where the oxygen is now connected to a hydrogen, but the carbon is still lacking an octet, it still has a positive charge. We can see that, okay, if we were to do resonance here, right, by giving a double bond to that carbon, giving it four bonds and taking away a lone pair from that oxygen, now the carbon has a fulfilled octet, has all eight. The oxygen is now missing a lone pair, right, but it still has its octet. It will now have the positive charge. And so this is still another form of stability where we are sharing the positive charge between both the carbon and the oxygen. But more importantly, this is still more stable due to octets, right? In this case, we have the oxygen and the carbon with fulfilled octets versus beforehand, it was just the oxygen. So, that being said, this is one of the most important concepts that we're going to be looking at through OCHEM, right? It is resonance. It's the movement of electrons between atoms through pi systems, which, if you haven't picked up on by now, pi systems are essentially double bonds, triple bonds, and lone pairs. We're going to take a much deeper look at those later on and actually define them very well. But for now, this is what we're going to be sort of talking about it as. And just remember that there are three different types of resonances. One with a lone pair with an adjacent atom that has multiple bonds. The second is a positive charge next to an atom with multiple bonds. And then the third and final is an atom with a positive charge adjacent to an atom with a lone pair or negative charge on it. So, hopefully this made sense. Next lecture, we're going to be looking at more examples of resonance, and we are also going to take a look at what we call invalid resonance structures so that you don't take a path that is a little incorrect. I'll see you all next time. Hopefully you enjoyed this lecture, and yeah, we'll see you later.